Okay, so today we're just going to do some review of the first chapter of Math 30-1. This is on transformations. So we're basically just going to look at how to move functions left, right, up, down, as well as stretch them vertically, stretch them horizontally, and reflect them. So today's plan is going to look like just, well, reviewing everything that we've done so far, because we have a quiz tomorrow, and the quiz is going to cover all that information. So chapter 1 concepts that we need to go over together will include function transformations. We're going to need to talk a little bit about mapping notation because that's very useful for moving individual points. And then we also have to talk about inverse functions. Basically how today is going to go is I'm going to put a bunch of different problems up that I will solve. You don't have to write them down. You can jot them down if you wish, but you don't have to because we've already done similar problems to this. But then about halfway through the lesson, I'm going to give you a selection of questions to try on your own. Once you're done trying them on your own, we'll go over them together as a class, and then you'll have some practice time towards the end. So the first thing we're going to talk about is function transformations. So in other words, just moving functions in all different directions as well as stretching them. We've talked about something called function notation. And the general form of function notation is y equals a times f of b times x minus h, and then plus k at the very end. When you have it in this form, your a value, the number that's on the outside of the whole thing, is the amount that you're going to be doing a vertical stretch by. So a vertical stretch by a factor of a. Now remember, a vertical stretch really just means you're multiplying your y values. Now another thing to notice is if your a value was negative, you'd be also doing a reflection in the x-axis, or in other words, a vertical reflection. The b value, the next number in there, is the strangest one of them all. It's a horizontal stretch, but it's actually by a factor of 1 over b. And just like before, if it was a negative number, you'd have a reflection in your y-axis, or in other words, a horizontal reflection. Now this b value is actually multiplying your x values by that 1 over b. So in other words, every one of your x values is going to be multiplied by 1 over b. So it'll be a horizontal stretch or a horizontal compress if it's going to be making it smaller. Now the h is basically just how much you're moving left or right. If h is greater than 0, the graph is going to be moving h units to the right, and if h is less than 0, the graph will move h units to the left. This can be a little bit confusing because remember, inside the standard function notation, we have x minus h. So if you have something like x minus positive 4, that would mean you're actually moving to the right by 4. Whereas if it said x plus 2 inside the function notation, remember x plus 2 is actually the same thing as saying x minus negative 2. So you'd be moving 2 units to the left instead. Now the last one, the k value, this one isn't quite as hard as the others, I would say. It just tells you how much you're moving up or down by. If it's a positive number, so if you're adding something, you're going up. If it's a negative number, you're going down. Now I can't stress exactly how important it is that you ensure you have nested brackets inside your function. And by nested brackets, I'm talking about this part right here. What the nested brackets do is it separates your b value, or in other words, your horizontal stretch, from your h value, which is your horizontal translation, how much you're moving left or right. If you didn't have your nested brackets, your h value isn't actually properly represented. So for example, if you had y equals f of 2x plus 4, we'll say, you might be tempted to look at this and go, oh, this is your h value, you're moving left 4. But that's not actually the case. This 2 needs to be outside of some brackets. And we can quite relatively easily change this. We just have to take this 2 and divide both of these terms by that 2. In other words, you could change this into f of, I'll use a square bracket just to separate this, 2 on the outside times x plus 4 divided by 2 is 2. And you can see that if you were to bounce this 2 back through the brackets, you get back exactly what you started with. But when it's in this form down here, it's a little nicer to interpret because then you can say, okay, you got your horizontal stretch piece. So you're doing a horizontal stretch by a factor of, well, remember it's a b value, so it's going to be 1 over b, so by 1 over 2. And then this inside the nested brackets is your h value. And usually it's supposed to be x minus h, so we know h is actually negative 2 here. Or more simply, we can just say you're going to go left 2. So with that, let's just do a really quick example. Again, I'll just walk you through this. You don't have to jot it down if you don't want. We want to describe the transformations that occur to f of x, given that g of x, so some new function, equals 4 times f of 3x plus 6 plus 2. If you take a look at this, if you were listening on that last slide, you might actually be able to tell what's a little funny with this. Notice inside, we don't actually have any nested brackets. Since we don't have any nested brackets, we're not going to get an accurate idea of where this function is going. So the first thing we should do before we start describing anything at all is change this function so that it has some nested brackets. So we'll say g of x is going to equal the 4 and the outside's not doing anything problematic, so we'll just leave it there. So 4f, I'll put a square bracket here and I'll pull out this b value. So it'll be 3, and then I'll put my nested bracket in there and say x plus, and this is where you have to think, 3 times what is going to give you 6? Or in other words, 6 divided by 3 gives you what? Well, it's going to be 2, right? So x plus 2 inside the nested brackets, close it off with a square one, and then the plus 2 on the outside is no problem. Now, if we're going to describe the transformations that are occurring to this, I always like describing them in the order that they occur. You might remember that the order that these transformations occur in is always your stretches or reflections first. The last thing that happens is your translation. So in other words, the last thing that happens is moving left, right, up, or down. So we'll start with this 4 on the outside here. This is your a value. Remember, your a value is a vertical stretch. So we can say the first thing happening to this is a vertical stretch. So a vert stir by 4. Next thing that will happen is this b value in here. That's your horizontal stretch. But remember, it's not by the b value, it's by 1 over b. So we can say this is a horizontal stretch by 1 over 3. Then we have our translations, our left, right, up, down. Inside here, we can see we have a plus 2. Since that's related to your h value, we can say that's going to be left 2. So left 2. And this plus 2 on the outside means you're going up 2. That is all you need to do when you're describing your transformations. Basically, just make sure you get it into a nested bracket form and then list out exactly what's happening step by step. Okay, so next we're going to talk really briefly about mapping notation. Remember, mapping notation is a really useful way of moving a certain point from the original function to its new transformed location. What I've done here is I've just kind of thrown all the transformations in both the x and the y direction together in one mapping notation form. Basically, what goes in mapping notation is exactly what you would say in words. So remember, when we say a horizontal stretch by 1 over b, that's what you're actually multiplying your x by. Just like if I said, oh, you're moving it to the right by 4 units, that would mean h is 4. That's what you're actually adding to your x components. Okay, so I know it's a little bit backwards. I know in function notation, if you saw plus 4, that would mean going to the left 4, but in mapping notation, it's the other way around. Since when you go right 4 on the x direction, if you're moving something, oh geez, that's awful, hold on. If you're going right 4 in the x direction, you're actually making your x value bigger. So if you had something at x equals 2, and you're moving it right 4 units, it's going to end up at 6, right? So you'd be adding 4 to it. The y values behave a little bit more how you would expect them to. The a value, which is your vertical stretch, is what's multiplying your y value, and then you're adding your k value to it. Next, I'd like just to briefly remind you about inverse functions. Recall that an inverse function, which we denoted using this form, f of negative 1x, is just where your x and your y coordinates are swapped. You just switch them, right? If you had an equation and you were going to say, oh, what's the equation of the inverse? All you have to do is you swap your x and your y's in that equation. So anytime you saw an x, change it to a y. Anytime you saw a y, change it to an x. And then rearrange it to isolate your new y variable. If you had a graph, so if I gave you a graph and said, oh, graph the inverse, just pick the graph apart piece by piece. So literally one coordinate at a time and swap your x and y's. It's time consuming, but it is a relatively simple process. You just find your coordinates and switch your x and y's and then plot them on the new graph. One thing that was really important is you can tell that the inverse of a function will itself be a function if the original function passes something called the horizontal line test. This is basically where if you had your graph let's say this was your graph. The horizontal line test says that if you draw a perfectly horizontal line anywhere on your graph, if it passes through the function more than once, then that means the inverse will not be a function. This little one that I just scribbled on right now, if you drew a horizontal line, let's say right here, notice it would be passing through a couple times. Now I know that's not exactly the most perfect horizontal line, but you get the idea. If I drew a horizontal line here, it's passing through, in this case, 1, 2, 3 times, certainly more than just once. So in other words, the inverse here would not be a function. So with that, I want you to try just some of the following questions that I will be putting up here. I'll actually have a handout here for you. I believe there's, let me just see, there's going to be 6 questions on this. How this is going to work is you'll be handed out the handout. I want you to try these questions ideally on your own. Try not to work on them with someone else. I want to see if you can be able to figure this out just on your own. We'll give you a fair amount of time to try these questions on your own, and then when we notice most, if not all of you are done, we'll go over them together. So again, also, if you finish these questions early and there's still some extra time, you can jump right into finishing your Chapter 1 assignment. Or if you're done that, you can do page 56, questions 1 to 15. That'll be a really good review of Chapter 1. So again, give these questions a shot. If this is being shown in the class right now, just pause and we'll go over these in just a few minutes. Okay, so hopefully you had some time to work on these. I'm going to go through them in the order that they were given. Very first one on the list is combining transformations. So this one wants you to write the transformation that has occurred to the following function, assuming that the base function is just y equals the square root of x, in the order that they occur. This one's kind of like the one we did early in this lesson, where we have a problem with nested brackets. Notice where your x was in the original base function. We now have 1/4 x plus 1. But there's no nested brackets there. Since there's no nested brackets there, we need to fix that problem first in order to get an accurate idea of where this function is going. So what I'll do is I'll say y equals -3 times the square root. I'll pull this 1/4 out because since that's what's multiplying your x, we can tell it's your b value, so 1/4. Then I'll put a nested bracket in here, x plus, this is where we're going to ask ourselves, 1/4 times what would equal 1? If it's a little easier, you can think of 1 divided by a quarter gives you what? Well, 1 divided by a quarter actually gives us 4, so it'll be x plus 4. Close the brackets off. I'll even make this square root a little longer so you can see it covers all of this. But then we have that -7 on the outside. So if we're comparing this to this base function, y equals the square root of x, we can see that we have an a value out in front. We have a b value in here. We have an h value of technically -4 inside of there because it's supposed to be x minus h, so it'd be -4 in there. And then we have a k value that's clearly -7 on the outside. So in the order that they occur, we can say that we have a vertical reflection because notice there's a negative in front of that. So I'll say a vertical reflection. Then we'll say, since it's part of the same number, that 3 there is a vertical stretch by 3. Then we have our b value, and remember the b value isn't what you're stretching horizontally by, it's the reciprocal of the b value. The reciprocal of the b value here, so the reciprocal of 1/4 is just 4. So we can say we have a horizontal stretch. So horizontal stretch, not by 1/4, but by 4. Then we can deal with our h and our k. Now since h is technically -4, or if you want to look at this, we have x plus 4, we can say we're moving left 4. And since k is -7, we can say we're going down 7. So in the next one, it gives us a graph showing what y equals g of x, our original function, looks like. It's asking us to draw the graph of the transformed function, given that y equals g times, g of -4x plus 12. Once again, and I bet I'm sounding like a broken record, there's no nested brackets here. We need to have nested brackets, otherwise we can't really figure out what is precisely going on. So what I'll do with this is I'll say we have y equals g of, let's pull that -4 out of there, so -4, nested bracket x, and then we have to think, okay, -4 times what would give us +12? Or you can think positive 12 divided by negative 4 gives you what? Well, the answer to that would be minus 3. So I'm actually going to change this so it says x minus 3. And you can always check your work to see if this is true by checking it back to the original by saying, you know what, negative 4, if it were to bounce through these brackets, it would give you negative 4x plus 12. That's the only transformations that are happening here. It might help you to put it into words. It is pretty quick. Notice we have a b value of negative 4. That tells us we have a horizontal reflection. We would also have a horizontal stretch. That's a z, horizontal stretch by 1 over 4. And since that's a minus 3 in that x there, we can say we're going right 3. Now, because we're we're drawing a new transformed graph, I think it would be really useful in this case to use mapping notation because we would probably want to move these points at a time. If you're someone who thinks they can go through these 3 steps here, horizontal reflection, horizontal stretch by a quarter, and right 3 without any other further calculations, by all means go for it. But for me, I like having something to fall back on, so I'd like to have some mapping notation written first. So here's how mapping notation would work. We can say in mapping notation, the original x and y will become something new. Now let's think about what's going to be happening to x. Since we're doing a horizontal reflection, we can instantly say we know we're multiplying x by a negative, right? Because a negative x is going to flip it horizontally to the other side of the graph. But we also know we're doing a horizontal stretch by 1 over 4. That means we're timesing all of our x components, or in other words, all of our x coordinates, by 1 over 4. Lastly, we're moving it right 3. Now this is where it's backwards compared to function notation, compared to this guy up here. If you're moving it right 3, what you're literally doing to your x coordinate is you're adding 3 to it, because you're going to be making it more to the positive side. It's going right on your grid. So with all of this in mind, we can say what's happening to our x coordinate is we're timesing it by negative 1 over 4. Right, because the negative is flipping it and the 1/4 is doing the horizontal stretch. So negative 1/4 x, and we're moving it right 3. So we're adding 3. And I know that's backwards to what function notation up here looks like. But in terms of what we're actually doing to a point, that's how it's moving. So anyway, negative 1/4 x plus 3, comma, here's the fun thing. We're not actually doing anything to our y values, so we can just leave y alone. Now, if you look at this graph that we have on the right, we have 4 coordinates that were given to us. First coordinate that's given to us is negative 6, 3. If we're going to perform the above operation to that, timesing negative 6 by negative 1/4 and then adding 3 actually gives us 4.5. And the y value will stay the same. So the y value will be 3. I'm going to plot that point first. So the first point is 4.53, which goes about right here on our graph. The next point we have on our graph is negative 4, negative 3. That's this point just down here. Negative 4, negative 3, so I'll put that one in. Negative 4, negative 3. And by throwing this into the above mapping notation equation, you're going to see that that point actually becomes the point 4, 3. Or sorry, 4, negative 3. My mistake. 4, negative 3. There we go. So 4, negative 3, that's going to be right here. And it would be useful to connect these dots because remember this dot and this dot were connected, so we might as well connect these dots. I'm going to apologize before I even do this because this is really hard on the trackpad I had, so I don't think this is going to be a straight line, but here we go. That's about as good as we're going to get. If you're doing this on your paper, of course, try to use a ruler. It makes it a little nicer. The next coordinate we're going to move is this one, nice and easy at 0, 0. Throwing 0, 0 into the above formula is going to give you 3, 0. So 3, 0 would be right here. And we'll connect that one with the previous dot. There we go. That wasn't too horrible. 3, 0. And then the last coordinate we have is 4, negative 4. So 4, negative 4. And if you throw that into the formula that we have, it's going to give you 2, negative 4. So in other words, we'll move that last point to 2, negative 4, and we'll connect it with the line we had before. And again, let's hope we can get a straight line. Yeah, not too bad. It works. So it's a little bit of a stretch of your imagination here, but if you can kind of see it, you can definitely see that we horizontally reflected it about our y-axis. So our y-axis served as like a mirror here. And then we stretched it by a quarter, so we made it 1/4 as wide as it used to be. And then we moved it to the right by 3 units. Okay, so this next one is a little bit more challenging than it looks, at least in my opinion. We have an original function. We want to transform it using g of x by vertically stretching it by a factor of 3, horizontally compressing it by a factor of 1/2. That's the same thing as saying horizontally stretching it. And then moving it right 6 units, and then that's it. So what I would do first, personally, now some people like just jumping right into this, but personally I like playing it a little bit more safe. I like writing it in function notation first. So I'm going to do that first. Function notation, we're going to say g of x is going to equal all of these modifications to f of x. So we're not going to refer to the equation itself, we're just going to refer to the f of x. Now remember, we talked about the general form of function notation with your a, b, h, and k. All you have to do is just throw those numbers in here. Function notation is a really good place to start. Since we have a vertical stretch by a factor of 3, that's going to be your a value. So we have 3f. We have a horizontal compression by a factor of 1/2. That's what you're multiplying your coordinates by. Your b value is the reciprocal of that. Don't fall for that trick. Your b value is the reciprocal of what you're actually multiplying your points by. And we know we're multiplying our points by because it says factor. So our b value in this case is actually 2. So it's f2, nested bracket, x, and then it's x minus h. Since we're moving it right 6 units, we know h is actually positive 6, so it's x minus 6. Close your nested bracket, close these ones off, and then that's it. We don't have to go any further with this. Now the next thing we need to do though, like we were done with function notation, the next thing we need to do is we actually need to write our equation for g of x. So we're actually doing it in terms of this. When you have function notation, basically what this means is the stuff inside the function, this piece right in here, is going to replace any x that you saw in your original equation. This 3 on the outside is going to multiply the entire thing. The whole original function is getting times by that 3. So in equation notation, what I'm going to get on this one is g of x equals 3 times the entire old function. So I might as well put big square brackets around this. And remember, anytime we saw in this original old function an x, we're going to change it with a 2 times x minus 6. So notice, I'll start my first bracket up. That would be like this bracket right here. Then we have an x. So inside that, I will put another bracket and say 2x minus 6 and close that off. This piece right here is like your old x. Okay, that's like your old x. Next up, we have plus 2, end that bracket off, square it, and then minus 5, and then end square brackets. This is an absolute mess. We're definitely going to want to clean this up a bit, especially this stuff on the inside here. So let's get at that. It's going to be gx equals 3, big bracket here, 2 times x minus 6. You might as well write that as 2x minus 12 plus 2 squared minus 5. And I guess then we can say g of x would equal 2x minus 10 squared minus 5. I don't really think we have any point in going much further with this. If you wish, you can bounce the 3 through. You could also pull this 2 out and have a whole nested bracket thing going on here. Really, the absolute maximum that I would do would be this next step. And honestly, the step you've just done, like this right here, totally okay for a final answer. But if I were to completely finish this off and have it in almost like a vertex form from what you would have done back in Math 20, is I would finish this off by saying it's 3 bracket 2 bracket x minus 5, because I can just divide the 2 away from this 10 here, and then end that bracket, squared, minus, and notice this 3 would technically hit this 5, so it'd be minus 15. That's a bit extreme, but that's about as far as I would ever expect you to go. I'd like you to go at least to here, But if you went to here, that's all right as well. Next question is going to go a lot quicker here. We're just looking to find the equation of the inverse of f of x equals 3x squared minus 4. Remember that f of x is just usually a fancy way of saying y, so we can say y equals 3x squared minus 4. To find the inverse of this, so I'll just do it over here. To find the inverse, remember we just switch your x and your y. So instantly we can just say x equals 3y squared minus 4. We want to get y all by itself, so we would start by adding 4 on both sides. So x plus 4 equals 3y squared. Then I would divide every single piece of this by 3. You have some choices here. Personally, what I'll do is I'll just leave the 1/3 on the outside. So it'll be 1/3 x plus 4 equals y squared. If you wanted to, again, that 1/3 could have bounced through. You could have said x over 3 plus 4 over 3. It doesn't make a difference to me. It's totally okay one way or another. Last but not least, though, we want to get y completely by itself, so we'll need to square root this. So the square root of 1 over 3 x plus 4 equals y. And that would be a good inverse function. So this right here is your f negative 1x. So in this one, first thing right out the gates is it's asking us if the inverse of this function will be a function itself. Well, remember the horizontal line test tells us this. Clearly looking at this graph, it's going to fail the horizontal line test. There's no way that's passing the horizontal line test. So we can very safely say no to that first question. So no to this bit up here. And then it says draw the graph of the inverse and state how the domain of the original function could be restricted. Well, let's draw the graph of the inverse first, and then we'll talk about that whole domain thing. Remember, to draw the graph of an inverse, basically just do it one point at a time. And personally, I think picking the vertex, so this guy down here, is probably the easiest. Notice the coordinate of this vertex is 1, negative 3. That means the coordinate of the vertex of your inverse would be the opposite of that, negative 3, 1. So negative 3, 1 is over here. Then do it one point at a time from there. Next point I can see is 2, negative 2. So that means on the inverse you'll have negative 2, 2. Another point that I see looks like 3, 1. So the next point would be 1, 3. You might also be pretty keen on this one rather than looking at it point by point. You can see that this is starting to turn it sideways. When you're turning it sideways, it still has to be symmetrical like this one. So this point that I drew over here at negative 2, 2 is going to have a symmetrical point at negative 2, 0. And this guy that I drew over here at 1, 3 is going to have a symmetrical point at 1, negative 3. So just down, oh wait, no, not quite 1, negative 3. Sorry, my mistake. Let's count it away from the vertex. My mistake. Here's the vertex. We're 2 away from the vertex. We need to be 2 away from the vertex there. It'll actually be over here. My mistake. I knew that was a little too wide. And I think that's more or less good enough. We don't have to be super perfect on this by any means. We'll just draw the rest of the function from here. So there, and this is hard on this board here. There we go, that's not too bad. So there and there, that's our inverse. Now very clearly, drawing that inverse, seeing it in the red ink there, that itself is definitely not a function, right? It would fail the vertical line test, so it knows itself is not a function. But if we wanted to restrict the domain of the original function so that that inverse that we drew would have been a function, basically all we have to do is just find the location on the original function that would have otherwise been a starting point between failing the horizontal line test. And in a quadratic graph, it's going to be your vertex. So if you were to cut your original graph off right here at the vertex, you wouldn't have any problem when you took the reciprocal, because it would pass the horizontal line test. Or sorry, not the reciprocal, the inverse, my mistake. Anyway, so what we have to do here is we have to pretty much cut off this entire left arm of the original function, because that's where we're going to start having some horizontal line test problems. To cut it off, it's just literally as easy as saying, okay, what's the x value at your vertex? Oh, it's x is 1. So we just want to keep our points where x are greater than or equal to 1. That's all you need to do. That's all you need to say to restrict the domain. So if we're keeping that, that means we're keeping this whole part of the original graph, but we're not keeping that other arm on the other side, right? So it's only that one side. That's restricting the domain so that if you were to take the inverse, you'd be keeping that arm, and therefore your inverse itself would be a function. Okay, so this last one is a diploma exam question. I took it straight off of a previous diploma exam that they've made public on the Alberta Education website. There's a couple different ways of doing this. I'll show you the two ways that I could think of right off the top of my head. I'll show you what I think is the easier way, and then I'll show you another way that works just as well, but it's just a little bit more work. The easy way to me is looking at my original function f of x and saying, okay, this function is in what we would have called in Math 20 vertex form. So we know we have a vertex at the coordinate 2, 1. So that one has a coordinate 2, 1 for its vertex. Even if you didn't remember that from Math 20, you might be able to notice that this f of x is just some sort of a transformation of the base function x squared, where you moved it right 2 and up 1. Well, hopefully you know on the base function x squared that the vertex is 0, 0. If you're moving 0, 0, right 2 and up 1, then 2, 1 is your vertex. Now, on g of x, which is what we're looking to find the vertex of, g of x is just a transformation of f of x. Notice the transformation it's doing is we're moving it right 4 and up 3. Well, if you move this vertex right 4 units and then up 3 units, you'd be getting to 6, 4, which very conveniently is one of the answers that was given. That is, in my opinion, the easier way of doing things. There's a more challenging way that I can think of, but still, fully reasonable, and that would be to pretty much use this g of x transformation and totally change f of x. What I mean by that is we can say that g of x in equation notation is going to be where we change any x that we saw in f of x with this x minus 4. So notice in f of x, right up here, we have in brackets x minus 2 squared. Well, we could change that to in brackets instead of x, we can have x minus 4, and then that minus 2, and bracket square it, plus 1. But then we need to have this plus 3 on the outside of the whole thing. Cleaning this up a little bit, if you clean up inside the brackets there, x minus 4 minus 2 gives us x minus 6 squared, plus, well, 1 plus 3 is 4. And like I mentioned before, from the whole vertex form conversation, or from this whole understanding that x squared as a base function has 0, 0 as a vertex, this is moving it right 6, up 4, so therefore 6, 4 would be your vertex. And we're all done. So what I want you to do for the rest of class is I want to make sure that you've completed your Chapter 1 assignment. Hand it in as soon as you're done. If you're not done it today, then please hand it in tomorrow at the absolute latest. If you're all done that assignment, it'd be really wise to work on page 56, questions 1 to 15. Focus on the areas where you struggle today. You don't have to do all of those questions. Skip any of the questions that you feel that you're very confident that you already know, and focus on the ones where you really need some extra practice. The quiz next class is going to cover the following things. Writing an equation for a transformed function, right? So in other words, if I say you're going left 4 and up 2 and you're doing a vertical stretch by 3 and all these things, you need to know how to make an equation from that. You're also going to need to know how to sketch a transformed function. We did a couple like that today here as well. You need to be able to describe transformations, so in other words, put it down in words what's happening. You need to know how to find inverses, and then there is going to be a diploma question, kind of like the one we just did just now. It's ripped straight from an old diploma exam. You will need to be able to tackle that one question. Now, the quiz is out of 16 marks in total. It's entirely written response except for the diploma question, which again is going to either be a multiple choice or a numerical response question. Anyway, if you ever need extra help, please let me know. I am available. Good luck.